All right, so now what we're going to do is we're going to take a look at kind of building some properties of integrals that we're going to use to actually evaluate integrals. Again, we're building toward these shortcuts that we want to be able to use in order to calculate these. And up to this point so far, what we've seen is that if we do have definite integrals to calculate, that we could use geometry, that if the function that we are using for our kind of derivative function inside the integral in the integrand position, that if that is a function that is geometric in nature, either linear so that you can break it into triangles or squares, or semicircle like this example right here, that we can calculate the definite integral by understanding the relationship between the definite integral and the area between the curve and the x-axis and use geometry formulas. We've also seen that we could also from the picture do exactly the same thing here to calculate it. Now we want to kind of jot down some very important properties that are going to allow us to maybe manipulate integrals to help us evaluate them as well. Now the first one probably should seem kind of common sense, but if I was going to have a function and the function has to be defined at a, so if I'm looking at any generic function f of x and it's defined at a, and I want to calculate the integral from a to a, well, this kind of plays on the idea that, if you're looking at a line has no thickness. A line has no area. So when you go from a to a, how much area have you accumulated? You've not accumulated anything. Have gone nowhere. So the definite integral from a to a will always be 0. Now, make sure you pay attention. That's different than if it's not defined. So, like for example, if I take a look over here, we were doing the definite integral on the signum function. If I try to do the definite integral from 0 to 0 on the signum function, this is going to be, does not exist or is undefined because you can't have an accumulation or even anything if it didn't exist. There's nothing there. And so that's a D&E. It has to actually exist when we're doing it. Now, this is also something I might want to mention right now, that this example right here especially is an example of the improper integrals, that it is an integral with an integrand that is undefined at a value within the interval, and that's really more of a BC topic. But as you can see here, there are cases like in this one where we can calculate an integral even though the integrand in the integration is undefined at x equal to 0. And like I said, and the reason here is if you work backwards to what this is the derivative of, it's actually the derivative of an absolute value function. So it sort of makes sense that you should be able to accumulate through the entire function that you're looking at. And so that's the idea, that some improper integrals you're going to be able to find the definite integral for, and some you will not. But we're showing you specifically examples that you can. All right, so that's property number 1. This one is the one we had before, that if you go forwards through the interval, it would be the opposite in sign from going backwards, that if you accumulate going forward, you would lose going backwards, so they would have opposite sign. Now, number 3 should be fairly kind of common sense for us too, that if I have a definite integral of a constant, so we basically have a rate function that is a constant coming across, and we're trying to accumulate area from A to B. And that if you were to accumulate this area, hopefully you're like, oh, well, this is nothing more than a rectangle of which the width is b minus a and the height is whatever the constant is. Whether it's above or below doesn't matter. It'll be positive or negative depending on whether c is above or below, and then the area is simply the height times b minus a. So that's a straightforward one that we use quite a bit. We'll come back to that later because this kind of leads into some of the findings that we're going to do for shortcuts. We also have this idea that if I am taking the accumulation on a sum of two functions, I can accumulate on the first function and add it to the accumulation for the second function. And that's basically because your rates are additive. You are adding your y values or your rates together. So of course, if you add your rates together, then you're going to accumulate together. So that should be common sense. If I have a constant inside of an integral, then I can pull it out when you have a constant times a function. And again, this can kind of, if you think about it, because this is our sum as I equals 1 to n of your delta x f of ci, and we're taking the limit as n goes to infinity. If I add a constant in here into this function, just multiply it by a constant, that constant is not the variable of integration, so you could pull it out of the summation. And it's also not the variable of the limit, which is n, so then I can pull it all the way out. And so you can essentially pull out your constants. So number 5 should make sense according to the rules that we've already learned. So the integration of a constant times a function, we can pull the constant out. And then we take a look at this idea here. And this is a very important idea. And you kind of already got this, that when we were talking about if I were to have, say, some positive and some negative values for a function. Like suppose this was my function. Here's A, here's B, and then here is C. That I basically, because I'm accumulating from A to B, it wouldn't matter if I break it up in the middle with the value C and accumulate from A to C and then add that to what do I accumulate from C to B, that this should make sense to us. But the trick here is to also realize that the C does not have to be between A and B. So if I had the same function between A and B, and then there was a C out here, okay, and the trick is that I want to calculate from A to B. What would happen if I accumulated all the way to C and then backed up back to B? Wouldn't you see that that's exactly the same as going from A to B this way? That you can break it up by breaking it up in the middle, or you can go too far past it and then come back because you're accumulating. You accumulate and then you take out the extra that you added. And likewise, it also works when you have your C value in the beginning. So if this is my A and my B, if C was back here, and whatever the function was doing coming back this way, if I go A to C, I'm taking out, well, in this case I'd be putting in because I'm going backwards and it's negative, so you would deaccumulate here and then go back forwards and you would put it right back in and then head on and accumulate. So all of these would give you exactly the accumulation from A to B. That doesn't matter whether C is in the middle, out on the right side, or over on the left side, that this is always true. It's kind of a convenient little fact that we employ whenever we want to. So you'll start to see some things where what they do is they give you certain intervals. The 0 to 10 is 17 and 0 to 8 is 12, and then they want you to find 8 to 10. So they're just playing on the trick that if I want to go 8 to 10, and I'm also got some things going on in here of 3f of x plus 2 dx, that the first thing I'm going to do is apply the properties and kind of I can distribute the integration over the sum and I can pull the constant out. So I go, okay, using the properties above, I need to do the integral from 8 to 10 of f of x dx times 3 and add to that the integral from 8 to 10 of 2 dx. So we kind of do this distribution of our integration through the sum and with the constant. And then we look at this and we go, well, the problem I have, this one is okay because over here, this is the integration of a constant function. So I pretty much know this one's going to be the height 2 times my b minus a, and we have that one taken care of. All right, now over here, I'm going to have to do a little bit more work. I'm going to back up a little bit and kind of separate this out because I don't know for this function f of x, 8 to 10 but I know 0 to 10, and I know 0 to 8. So thinking about this, that if I wanted to do 8 to 10, I could split this up by choosing a value to go 8 to something, f of x dx, and then go from that something to 10, f of x dx. And so then I go, well, what would be a good value to go to? And I look at what I know, and I'm going to go, because 0, this is 0 to 10, so I'm going to use 0 and 0 here. Now, it may be bothering you at the moment that this is 8 to 0, and I don't know 8 to 0, but remember, if you know 0 to 8, you actually do know 8 to 0 because it's going backwards in your interval. So we would do 3 times the integral from 8 to 0 is the opposite of the integral from 0 to 8, so then we could put a negative 12 there. And then we have 0 to 10 is 17, plus our 2 times 2 are 4 over here, and then we are essentially just arithmetic to calculate. We get 15 plus 4, or 19. So you can see how if you know certain integrals, you can work through them and basically create other integrals by using these properties. All right, example 13, another example where I have an improper integral. I have a division by 0 at x equal to 3. So this is discontinuous. But again, they're saying we can sometimes calculate these improper integrals using the area of the region. So maybe I need to graph it in order to see what's going on. Now what we need to notice that if I'm going to graph this f of x, 9 minus x squared over x minus 3, using your Algebra 2 skills, this is 3 plus x, 3 minus x, all over x minus 3. And just with a little factoring here, I'm going to pull a negative out of this factor. So I'm going to have x minus 3 negative. I'm just pulling the negative out and then putting that first. X plus 3 over x minus 3, which is going to give me, after I cancel and remove the discontinuity, negative x plus 3. So what we have here is basically a linear function with a removable discontinuity, with a hole, a point discontinuity, at x equal to 3, and our location is going to be negative 6, is going to be the location of that hole. So I'm going to go ahead and graph it just to kind of show you what we're looking at, and that's why we can use geometry on this, because it was a linear. We have negative 3 is going to be our y-intercept. Since I want to go negative 5, negative 5 plus 3 would be negative 2, would give me 2. And then I'm also going to do 6. 6 plus 3 is 9, so we'd be at negative 9 when I am at 6. All right, and then we have this hole at 3 and 3 negative 6. And so this is essentially the portion of the graph that I'm trying to find the area, well, the accumulated area between the function and the x-axis. So then I go, all right, well, what am I accumulating? Here's the accumulation starting out. Then we start losing, okay? And does it bother me that this is kind of missing right there? Actually, not really, because this is an example of an improper integral where it doesn't bother me for the accumulation that this actually is going to just add the area, and we'll skip over the part that's not existent right there, and then we'll keep going until we get to this over here. And it doesn't bother me that that's missing, because you're basically missing something that doesn't affect the actual sum of the area. So I basically just need to find these areas and then positive and negative to calculate my integral. So this had a base of 2 and a height of 2, so the area would be 1/2 of 2 times 2, 1/2 of 4, or 2. The area over here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So 1/2 of 9, and then our negative 9. So that's going to give me negative 81 over 2. Well, actually, the area is positive. But when I want to calculate my definite integral from negative 5 to 6 of this 9 minus x squared over x minus 3 dx, I know that I'm going to add this area in, and then I'm going to subtract that area out to get my final answer, which I do believe is negative 77 over 2, and you can make it negative 38.5 if you would like, negative 38.5. So even though this is missing a value in the middle, it doesn't affect it. This is an example of an improper integral where we could basically just calculate the accumulation of error, and that missing a single value does not bother me at all. All right, now let's take a look at the next problem, the next example. All right, so in this one, this is another idea of using given information in order to calculate things, and the fact that there's symmetry. Now, the fact that they're giving me here that the integral from 0 to pi, and this is your sine graph, so you should know your values here. Here's pi over 2, this would be negative pi over 2, and so on, that this area right here has an area of 2. And we know that the sine function is an odd function, so that it is symmetric over the origin, so we pretty much know that the area over here is 2 also. So we'll keep that in mind, and we'll start calculating some of these integrals that we have below. So here I want the integral from pi to 2 pi. Well, you're like, well, I didn't graph it, but don't we know what that looks like? We can continue this graph on and continue the repeating pattern of our sine graph to 2 pi. What we need to remember is that this is now below the x-axis, so the definite integral is going to be a negative number, so we would go negative 2. If I want to go 0 to 2 pi, I am accumulating an area of 2, and then I'm losing an area of 2, so clearly we would have 0. If I'm going to go from pi to pi over 2, now two things are going on here. Remember, you're going backwards, and you're only going backwards for half of this shaded region. So I went backwards for an area of 1, so that would be negative 1. So again, you just got to know whether it's positive or negative. All right, now over here, this is saying that I want to take the, and this is where you have to be careful, okay? Don't just add 2 to 2 and get 4. You got to remember your properties, that if I'm going to integrate over a sum, I have to take the integral from 0 to pi of 2 dx plus the integral from 0 to pi on sine of x dx. And then I use the property that the integral of a constant would be 2 times pi minus 0 plus the integral from 0 to pi, which is our 2, and so we end up with a final answer of 2 pi plus 2. So don't fall into the trap of going, oh, I just added 2, so it's going to be 4. Make sure you are applying the properties that we just talked about on the previous page. All right. Now, what about this? We have a constant times the function. Well, that one's easy. All you have to do is pull the constant out, 0 to pi, sine of x dx, and so we can do twice the integral times 2. That one is 4 when we're looking at it. All right, so those are kind of pretty straightforward problems coming across. Now, let's take a look at the next one. Now, I'm going to do this kind of geometrically, kind of using transformations, because I'm going to think of this with a transformational approach. And then I'm going to show you kind of an idea of a U substitution approach that kind of achieves the same thing. And then you can, at this point, because we're so early in it, the transformation approach is usually enough for a problem like this, but later on the U substitution will come back into play. So the first thing is you look at this and you think, well, what does this do to the graph that we had above? That if I were to graph f of x equal to sine of x minus 2, that this is y equals sine of x shifted to the right 2. So I know that the graph that I had above, okay, I'll just kind of add it in kind of dotted, which was looking like this. And we'll go back. Where this was my negative pi, here was 0, this is pi, and that's 2 pi. That what I'm doing to this graph is I'm shifting it to the right 2. Okay, pi is about 3.14, so shifting it right 2 might shift it to here. So every point, this will now be pi plus 2. This would be 2 pi plus 2. And going back this way, this would now be negative pi plus 2. So the actual function that I'm looking at is this green one. So now all I did was I basically thought about it in terms of transformation. And then I look at my integral, my bounds on the integral. I'm going from 2 to pi plus 2. So I'm going from 2 to pi plus 2. Oh, well, that's nothing more than the piece I had here shifted over. So the answer is it's going to be 2. So that's my transformation approach to that. All right, let's do the same thing for the next one. If I were to look at the function and define the function f of x as sine of x over 2, then basically I know that that is going to be y equals sine of x that has been stretched horizontally by 2. It's twice as wide. So if I'm going to take a quick look at the sketch of that just to kind of see what happens. And again, we have our original one. I'm just going to do this side of it this time. All right, so we had our pi, and let's make it a little bit more reasonable here, 2 pi. And so that's the original. And so what we've done is we've done it so that we've stretched everything by 2. So this pi will now be over here. This height, which was at pi over 2, will now be at pi. So what I've done is stretched it out so that I'm only looking at this portion of the graph. I'm going 0 to 2 pi. So this is what I'm trying to calculate our area. Now let's think about what happens when we do a horizontal stretch to a region and what happens to its area. If I had a triangle and I kept the height the same and I make it twice as wide, how would that affect the area? This area is 1/2 base times height. This base is twice that base, so it's 1/2 2b times. So if this is b, this is 2b. The h is the same in both of them. Couldn't you agree that the area is twice as big? If I had a rectangle and I made it twice as wide, kept the height the same. This is b, this is 2b, the heights are the same. Can we kind of agree that it makes sense to us that when all you do is stretch out, even if it's an irregular region like this one, the heights are the same. Remember, we're summing up all the rectangles. They will all have all the same heights. The only difference is the b minus a is twice as wide. So it will end up being twice the area that it was before. So the answer is 4. All right. Now here I'm going negative pi to pi. Now let's think about this odd function. We can go back up here to this. This one's not a transformation. This one is, if I go negative pi to pi, it's an odd function. What would always be true for an odd function if you are equidistant bounds, a left bound and a right bound on either side of the origin? Hopefully you'd see that that always ends up being equal to 0. Okay, so if f of x is odd, the integral from negative a to a of f of x dx is always going to be equal to 0 if the function is odd. All right, and then we get over here and we come into cosine. Now, the trick here is to realize that cosine is nothing more than a transformation of a sine graph. It's the same essential shape, but it has been shifted. So that's why we're thinking about this as a transformation approach. If I just think of that in loose terms, my cosine graph, okay, looks like this, but it's basically the sine graph shifted over. So if I were to ask you what this area is right here, because it's nothing more than the sine graph shifted over, that would have an area of 2. And if I'm going 0 to pi, here's my pi over 2 and here's my pi, hopefully it doesn't even really matter what I am actually calculating, that I didn't really need to know that this was 2 because I have accumulated and then I lost exactly the same area. So that's going to be 0. And then likewise over here for 0 to 2 pi, because this one is above and then below, and then we get below a little bit more and then we're above again, hopefully you can see that this one is equal to 0 as well. All right, but now let's think about this a different way. It's kind of previewing what's going to be coming in another section. Right here, I know that the integral from 0 to pi of sine of x dx is equal to 2. That's what I know. All right. One of the things that we can do is we can basically do a u substitution. Now, this is a comment about the variables that you're integrating with respect to. Does it really matter what variable I call the x-axis? I could rewrite this as 0 to pi sine u du, right? That would still be equal to 2. It doesn't really matter what name I'm calling my input. I can name it anything that I want. So the trick here is to take a look above and say, I don't really like this x minus 2 in here. So I'm going to let u equal x minus 2. All right. Then I calculate the derivative of u. Du with respect to x is going to equal 1 dx dx, which is 1. Now, but then I want to write this in differential form. The differential in u is exactly equal to the differential in x. So what that's going to allow me to start to do is to take this problem up here. Okay, so all I'm doing right here is some pre-work. That I'm going to be able to take the problem, the integral, I'll put the bounds on in a second, this sine, or well, actually we'll do this, 2 pi plus 2, x minus 2 dx, and I start to rewrite this, transform it, kind of like untransform it, as sine of u. I do a u substitution. But I learned when I did my derivative of u with respect to x that du and dx are the same, so I can take dx out and put du in its place. And remember, these bounds are the bounds on x. You are going from x equal to 2 up to x equal to pi plus 2. And so what we're going to need to do, because we're changing our variable, we're doing a u substitution, I need to find u in terms of x. U is x minus 2. So if u is x minus 2, it would be 2 minus 2, or 0 would be the bound for u. And then u would equal pi plus 2 minus 2, which would give me pi. And you can see that by kind of removing the transformation, we see that we still have the same area that we had before, which is 2. It's another approach to this, something that will come in handy later on down the road to take problems that are complicated, to take out some of these transformations that occur, and to turn it into an easier problem that we can integrate fairly quickly. Okay? Another comment about, say, the cosine ones up here, and this is more, trig identities always come into play, that I could have done this problem the much similar way and said that if I have 0 to 2 pi, that you could think of the cosine graph as nothing more than a transformation of the sine graph. So cosine is sine of pi over 2 minus x dx. We can actually do a trig substitution in there. And I don't know why this is having some issues. That when we're looking at this, that we can then apply the transformation approach or apply a u substitution to work this problem as well. Although at this point, because these are so easy, I would probably not go ahead and do that for these problems. I would simply use the transformation approach. All right, so that'll wrap up these examples, and we'll start practicing in class next time. So that's the end of what I wanted to discuss with 5.3.